Hello, and welcome back to another IB Math Speedrun with me, Vince. In today's speedrun, we're going to be going through chapter 10.1, which is all about the different forms of a complex number. So let's jump right in. So we already know one form of the complex number. That's where we have a plus bi. And this is, the easiest form to recognize, where we have a complex number z equals a plus bi. But there are two more forms that we need to know about, and it's helpful to plot a graph to show this. So if we're getting a complex number, remember this is the real number plane, this is the imaginary number plane, then this point here is a, and this point here is b, and so that's how we define the number. But there are more than one way to do this. So the second way we need to know about is equal to the argument, the modulus argument method of defining a number. And so that's where we have, we define a number by our CIS theta. And this is shorthand for writing r cosine theta plus I sine theta. So this is called a modulus argument form. Well, why is it called a modulus argument form? Because instead of taking in two real numbers as the coordinates, instead we are taking in the modulus and the argument. So the argument is, if we draw the line here, the argument is this angle between the x-axis or the real number plane and the number, and the modulus, which is r, is effectively the magnitude of the number. And so this is called the modulus argument form, or the polar form of a complex number. And so finally, there's one last form we need to know about, and it's called Euler's form, or the exponential form of a complex number. So there are, two ways to define this. This is one of the ways. So if we have a function of I theta, which is equal to e to the I theta, right? Well, we can expand this as a Maclaurin series. So this is equal as the sum from k is equal to 0 to infinity of 1 plus I theta plus I theta squared over 2 factorial plus and so on. And the thing is, we can group these terms. So this is equal to the sum, so this is equal to 1 minus I theta squared over 2 factorial plus I theta to the 4 over 4 factorial and so on, plus I times, this is minus here because I squared is equal to negative 1. So we can remove I from here. And so this is 1 plus theta squared over 2 minus theta squared over 2 plus theta squared over 4 and so on. And then plus I, and then over here we have theta minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial. And what you might notice is that this simplifies into sine theta, simplifies into cosine theta because this is the expansion of cosine theta, and this is plus I sine theta. So actually, we have e to the I theta is equal to cosine theta plus I sine theta. And if you've ever heard of the very important formula, e to the I pi is equal to 1, well, this is where it comes from, because we have e to the I pi is equal to cosine pi, which is negative 1, plus I sine pi, which is 0. So we have e to the I pi equals negative 1, and so that's where this comes from. So this is the third form we need to know about, and it's called the exponential or Euler's form. And so e to the I theta is actually equal to cosine theta plus I sine theta, which is equal, of course, to a plus bi. So two complex numbers in polar form are equal, of course, if their moduli are equal and their arguments are equal or differ by a multiple of 2 pi. And so yeah, so some other things to talk about is if we are plotting, because in this chapter we're going to do a lot of plots of imaginary numbers. So if we have an imaginary number z over here, its conjugate is simply the coordinate mirrored in the y-axis. So this is the conjugate of z. And the negative value is, of course, going to be the part opposite the diameter. And then the negative conjugate will be here. And then, of course, we return to the original number. So with that being said, let's jump into some questions. So first, we have draw the complex numbers in the coordinate system given by the modulus and argument. So first, we have the argument is equal to 1 and argz is equal to pi. Third, we have the modulus of z is equal to 5 and the argument of z is equal to pi over 2. Next, we have the modulus of z is equal to 1/2 and argz is equal to 5 over 4 pi. And so this is almost as simple as graphing numbers in like a unit circle. So I'll just do them all in one graph. How we do it normally is, first, if we get the modulus is 1, we will draw a circle with radius 1. And then the argument of z is pi. So pi would be over here, so this is that point. So this is z1. Next, the modulus of z is 5, so of course not to scale. Actually, I'll just use the same circle. But, of course, you would draw a bigger circle normally or change the axes. And argument of z is pi over 2, so the angle theta is pi over 2 over here, so this is z. Finally, z is 1/2, so a much smaller circle, and the argument of z is 5 over 4 pi. So this would be around here, so this would be z. Okay, on to the next question, where we need to find the following complex numbers in polar form. So first 2 plus 2i, next -4 minus 3i, minus 3i, that's actually the third one. E is 21 minus 20i, and g is equal to square root 2 over 3 minus square root 2 over 4i. Okay, let's find these forms in polar form. So we have 2 plus 2i. And so how do we convert this 2 plus 2i to polar form is the question. So we know that this is equal to r cosine theta plus I sine theta. So we have r cosine theta is equal to 2 and r sine theta is equal to 2. So we have cosine theta is sine theta. So therefore tangent of theta is 1, so theta is equal to pi over 4. So r times square root 2 over 2 is equal to 2. That's what we're saying here. So r must be equal to the square root of 2. So to express this in polar form, this is equal to square root of 2 cis pi over 4. This is it in polar form. Okay, next one. We have -4 minus 3i. So r cosine theta is equal to -4. R sine theta is equal to -3, I think. And so, well, how do we do this? We have to divide this by that. And so we effectively get tangent theta is equal to 3/4. So theta must equal the inverse tangent of 3/4, radians 3/4. So this is equal to 0.64. And so if we substitute this in here, we can simply solve that r sine 0.64 is equal to -3. So therefore r is equal to, let's get the sine of this, which is 0.6. So we have r times 0.6 is -3. R is -3 divided by 0.6. So r is equal to -5. So this is equal to -5 cis 0.64. Okay, next we have 21 minus 20i. So we have r sine theta is equal to negative 20. R cosine theta is equal to 21. So tan theta is equal to negative 20 over 21. So theta is equal to tangent of negative 1 of 20, negative 20 divided by 21, which is of a negative value. And okay, some textbooks will allow you to do values of the argument from negative pi to pi. Some will give them from 0 to 2 pi. It doesn't matter too much. But I'm going to make this positive. So this is going to be 2.38. So finally we have r sine 2.38 is equal to negative 20. So r is equal to the sine of this. And then it's negative 20 divided by the sine, which is equal to negative 29. So we have negative 29 CIS 2.38 is our answer. And finally, we have square root 2 over 3 minus square root 2 over 4i. So what we have here is r sine theta is equal to negative square root 2 over 4, and r cosine theta is equal to square root 2 over 3. So tangent of theta is actually equal to negative 3/4. So theta is equal to negative 3/4 is equal to, I'll add pi to make that positive, it's equal to 2.5 more or less. And so we can plug this in. So r sine 2.5 is equal to negative root 2 over 4. So r is equal to sine that. So it's negative root 2 divided by 4 divided by 0.6. So I'm getting r is equal to negative, is around 0.589, negative 0.589, which is probably a third, but it's okay. 0.589 CIS 2.5 should be our answer. Nice. Okay, so the third question, find the Cartesian form of the complex numbers in question 1. So we need to find the Cartesian form first of modulus z is 1. So we have CIS pi more or less. We need to find this in the Cartesian form. And this one we don't even need to use a calculator because this will simply be equal to negative 1. It's just negative 1 on the number line. Remember, if we plot it, this point is equal to here, and so it's simply equal to negative 1 with no imaginary part, since of course sine pi is equal to 0. So that's negative 1. So the next one we need to find is equal to 5 CIS 5 pi over 3. Oh, I must have missed the question. No, yeah, okay. So how do we find this in the normal form? Well, we can write this as a plus bi, where a is equal to 5 cosine 5 pi over 3 plus 5 sine 5 pi over 3i. So cosine 5 pi over 3, ooh, what is this? This is equal to 1/2, I believe. So this is 5 over 2. Cosine 5 pi over 3 should be equal to 1/2. Let me just check. Cosine 5 pi over 3. Yeah, it's equal to 1/2. So we have 5 over 2 plus 5 times root 3 over 2 times I. So this will be converting the number from polar to a normal form. I mean polar to Cartesian. Okay, and finally we have 1/2 CIS 5 pi over 4. So this is equal to 1/2 cosine 5 pi over 4 plus 1/2 sine 5 pi over 4 I. So this is equal to, well, what's cosine 5 pi over 4? cosine 5 pi over 4 will be equal to negative root 2 over 2. So this is negative root 2 over 4. And then this is also minus root 2 over 4i. I believe, yeah. Nice. Okay. So finally, we need to, given the complex number, z is equal to 7 over 12 e to the I pi over 9. We need to find in polar form negative z and negative z modulus. And so the trick is, of course, here, this is simply equal to 7 over 12 cis pi over 9. So we need to find the negative value, so that's negative 7 over 12 cis pi over 9, and the negative modulus. So the negative modulus, here's a trick, is equal to, if we rotate this complex number pi degrees, if we need to get the negative modulus of, if we need to get the negative modulus of a number, and we actually have the negative number. So we can simply say that the negative modulus is equal to negative 7 over 12 cis, and then we have to add pi. So this would be 10 pi over 9 degrees. Well, not degrees, radians. Oh, sorry, sorry. I've made a mistake. This should be 7 over 12 cis. Wait, no, I haven't made a mistake. This should be negative pi over 9. Why have they labeled it as 7 over 12 cis pi over 9? That's a bit odd. Oh, but this is minus I sine beta. Huh? This is very weird. This should be negative pi over 9, and this one should be negative pi over 9. That is odd indeed. This is odd. But anyways, that was all for the speedrun. I hope you enjoyed it. Wait, no. Yeah, no, this is correct. Okay, so that was all for the speedrun. I hope you enjoyed. I hope to see you in the next one. So, see you then.